You can ask any questions. Okay, we are now recording. Questions? Okay, so let us start with today's lecture. And I hope you have seen the Moodle. It's now up. Announcements and so on will be made there. All right. So let us start by discussing a little bit about the place of electrodynamics among the forces of nature. So as you know, there are 4 forces of nature: gravity, electrodynamics, strong and weak nuclear forces. And so now let us try to understand where electrodynamics fits into these 4 forces. So let me start by asking, which of these forces is stronger? Is it electrodynamics? So it is electrodynamics versus gravitation. And which is stronger? This is our version of Batman versus Superman. Which of these forces? So how many of you think gravitation is stronger? Raise your hands. How many of you think electrodynamics is the stronger force? Okay, I have a lot of hands. Are these these are voting for gravitation? Are you people voting for gravitation? Okay, I'm assuming everyone is. We have 50 people voting for gravitation. How many of you think electrodynamics is the stronger force? Let's hear it for electrodynamics. Okay, roughly comparable amounts. The class is divided between electrodynamics and gravitation. So let's see. Let us now calculate which of this is stronger. So we want to calculate gravitation by force, by electrodynamics. So how do we even compare? So what is the gravitational force between 2 masses? It's given by G m1 m2 by r square. The magnitude of the force, that is what we are comparing. And electrostatic force is 1 by 4 pi epsilon naught q1 q2 by r square. So let us compare these 2 forces between, let us say, 2 electrons separated by the same distance. That would make sense. That would give us a comparison. 2 things, 2 same things, and let us check what the gravitational force on it is and what the electrostatic force on it is. So Fg by Fe, and we're doing it for 2 electrons. So this is G, both are electrons, so m square divided by q1, q2, 4 pi epsilon naught. Notice that r square has gotten cancelled because both fall off as 1 over r square. So the r square part has got cancelled. We now have to deal only with the constants. So let us estimate the constants. We don't need to be too precise. We want to get an order of magnitude estimate. So G Newton, gravitational constant is, I think, 6.6 into 10 to the minus 11 Newton per meter square per kg square. So let's just call it 10 to the minus 11. Electron mass is 9 into 10 to the minus 31 kg. So it's almost like 10 into 10 to the minus 31. So just write it as 10 to the power minus 30 square. 4 into pi is roughly 10. Epsilon naught is roughly 8.85 into 10 to the minus 12, so roughly 10 to the minus 11. Charge is 1.6 into 10 to the minus 19 square. 1.6 we can neglect for our purposes of getting an order of magnitude estimate. This is something very important in physics. We often try to get just simple order of magnitude estimates. We don't worry about the exact numbers, just try to get an estimate. Okay, have I missed anything here? You can tell me in the comments if I've missed any factors. Let's see, I got G, I've got M square, I've got 4 pi epsilon naught, I've got Q1, Q2, Q square. Okay, so how much is this? This is 10 to the minus 11 into 10 to the minus 60 into 10 to the minus 10 divided by 10 to the power minus 38. How much is this? 171.81 minus 10 to the power minus 43. This is an order of magnitude estimate. And this is roughly correct. I think the correct number is 2 point something into 10 to the power minus 43. So we got a pretty good estimate here. And so this tells us that the force of gravity is much, much smaller than the force of electrodynamics. So gravity is very, very weak. So all of you who said gravity, just you got destroyed completely. The electrodynamics people have won this one with a margin of 10 to the power 43 factors. Okay. So now the question is, if electrodynamics is so much stronger than gravity, right? So if I have, so this was between 2 electrons. Alternately, I could have an electron and proton that will not change things much. A proton is like 1,000 times heavier than an electron. So one of these factors changes into 10 to the power 3 for 1 electron, 1 proton, and into 10 to the power 6 for 2 protons. There's a, okay, let me now pause and take the question. Yes. Go ahead and ask.
So sorry, it was by mistake.
No, okay. No questions. Okay, so if I have 2 electrons over here, then the force of gravity between them, there are 2 forces acting. Gravity is attracting them because they both have mass, but electrostatic repulsion is pushing them apart. And obviously electrostatic repulsion is going to win by a huge margin. So then we must ask, how did we ever discover gravity? If it is always like in this scenario that I just showed you, any gravitational force is going to be masked by the strong electrostatic repulsion. We would not even know that a tiny gravitational force was acting. I mean, you would have to go, if we measure the forces, gravity would appear after a fraction of 1 to the power 10 to the 43. So how do we know? How can you possibly detect gravity? That is the question. Force between 2 planets, each having charge, is 1 coulomb. Why is each planet having charge 1 coulomb? So I think that is a step in the right direction, but can anyone else? Taking net charge as 0 on both sides, very good. So, because most of the things that we see, atoms, yes, when charges are 0. Because the world is made up of atoms, and atoms are charge neutral. So they have 0 charge. So obviously, because they have 0 charge, they do not show electrostatic interactions at sufficient distances. So the dominating force for any large-scale interaction is actually gravitation. So someone asked me yesterday about, so I said that, so I just said that neutral, if things are neutral, there is no electrostatic interaction between them. That is true when they're at large distances. You should remember that when two things are close together, even if each of the things are neutral, there can definitely be some repulsion, some attraction between them. So consider this example. Let's say this is a minus charge and this is a plus charge. At some distance d, this whole thing is neutral. Let me put plus charge and minus charge at a distance d. Another of these things, you may have seen these things before, they're called dipoles. And suppose they are separated by a distance r. So there are a lot of forces acting here. One is the repulsion between the two positive charges, and that has a, so all the charges are equal, let us say. So this will be proportional to 1 over r square. And the repulsion between the two negative charges, that will be proportional to r plus 2d square. And minus the two repulsions, two attractions between negative and positive, acting in the opposite direction, 2r plus d square. And this need not cancel. So even though each of these dipoles is electrically neutral, it need not be true that there is absolutely zero interaction between them. There can be some net force. Of course, if r is very large compared to d, so we write r greater than d. I don't know if you have seen this symbol before, but this means that r is much larger than d. So d can be effectively neglected when we are talking about r. And so in that case, r plus d is almost equal to r. Roughly saying, like if r is 10 and d is 0.001, then r plus d is too close to 10 for us to consider that 0.001. Similarly, r plus 2d is also very close to r. And in this scenario, we have this force canceling out. So neutral objects at large distances will always, their forces will always be negligible. But at close distances, atoms can have some electrostatic interactions, and indeed they do. And some atomic and molecular interactions are modeled by interactions between dipoles. So someone asked me yesterday about the origin of normal forces, the force you get when you push against a wall. That is different. That mainly comes from a quantum mechanical principle called Pauli exclusion principle, which says that you cannot push two electrons too close together, but there can also be electrostatic forces between atoms and molecules close together when they're at close distance. Let me now pause for questions. What questions do you have? Yes, Monica, go ahead.
No, sir, that was a mistake.
No, no problem. All right, then let us do some problems. Let us solve some problems now.
Hello.
Yes, that's the question. Yeah, go ahead.
If we place a proton and two electrons around it in some in a random positions, initially at rest, then after attaining the stability, will they keep rotating or just stay in an equilibrium points? It's a bit confusing for me.
I do not
Thinking
understand, because there can be a equilibrium with electrons rotating, and there can be but I don't see how they can be in equilibrium with everything at rest. You're saying that the forces exactly cancel, something like that?
Yes, sir. Will they come to a rest and attain the equilibrium, or they just keep on rotating and just like in an atom?
I mean, it depends on the initial conditions.
So like
So like Earth and Sun are stable, rotating around each other.
so let us assume it is kept in an hypothetically isolated field.
Mhm.
Then what is the scene over there, sir?
I think you would have to formulate the question a bit more precisely. What do you mean by
Yes,
what is kept in
let
isolation?
us let us assume an isolated space which is free of any other external fields. Then
Mhm.
inside it, we just place one proton at the center and two electrons around it in
Mhm.
some other coordinates, or theta phi in some other coordinates.
Mhm.
Then will they just come to a rest by cancelling the forces and just attain some equilibrium positions, or they just keep on attain the stability and keep on rotating as in an atom? How will be the final states of it after attaining the stability?
Are the electrons at okay? Let us do this. Let us not discuss this in class. I will have some office hours. We can discuss particular problems like this in the office hours. Okay, so you can
Oh, okay, sir.
come
Thank
online
you.
and discuss with me.
Yes, sir.
Well, let us proceed with the class. If you have something not understanding in class, you can ask now. Problems we can discuss. We can discuss after class also, or we can discuss at some other office hours. Okay. Any other questions? Can charge bend any field like mass do? So space-time field? No. So mass bending space-time is general relativity, charge. We don't have a similar theory for charge. Okay, so let me just, we did gravity, but let me talk about another force. Okay, let me pose this question. In the nucleus, we know protons, there are a bunch of protons and neutrons. Now, protons repel each other by electrostatic repulsion. So how is it that protons are held together? And we have seen that electrostatic repulsion is pretty strong, much stronger than gravity at least. So what is the force or the mechanism that holds protons together in a nucleus? Nuclear binding forces, nuclear forces, yes. So there are two of them. Do you know which one? The strong nuclear force. That is correct. So the nuclear force, strong nuclear force is quite strong, and it binds protons with protons, protons with neutrons, neutrons with neutrons. But if that force is so strong, how is it that we ever detected electrostatics in the first place? Because if a force is much stronger than electrostatics, it should mask electrostatic forces. I hope you understand the question. Yes, a lot of people have said the correct answer. Very good. Which is that this is a short range force. Nuclear force does overcome the electrostatic force at short distances, but not at large distances. So it has a range of roughly 10 to the minus 15 meters. After this, it becomes weak. So we can model the strong nuclear force as kind of like going as having this kind of dependence on distance, where R naught is the range to minus 15 meters. This is not exact. When we talk about strong and weak nuclear forces, we have to describe them using quantum field theories, and the concept of force does not exist there. Nevertheless, this is a good description for certain distance ranges. And it says that the force falls off as e to the power minus r by r naught. And comparing, so this is the strong nuclear force. Compare it with electron, which goes as electrostatic repulsion, k by r square. This A by K ratio is large, so it's roughly like 137. This force is 137 times stronger than electrostatics. And so this tells you that initially at smaller distances, the strong nuclear force will be stronger, but it falls off pretty quickly. It falls off quicker than 1 over r squared. It falls off exponentially. So after r greater than r naught, it will fall off very, very quickly. And then at large distances, it is electrostatic repulsion that will dominate. So if you plot this as a graph, you will get something like that. Goes up and then it falls down very quickly. And after a certain distance, it is all the effect of strong nuclear force compared to electrostatic force will be completely negligible. But there's a short distance where this dominates. Okay, good. Now let us do some exercises. Let us get back from all this talk about strong and weak nuclear forces. Get back to some simple exercises. So what do I have? Let's calculate the force due to a ring of charge. Okay. So let's calculate the force at a point over the center of the ring at some distance z over the ring, and the ring has a radius r, and it has a charge density, charge per unit length, which is lambda. How am I doing for time? Okay. So how do I do this? We divide this ring into infinitesimal pieces of length dl. So this is a piece of length dl, and the charge it carries is lambda dl. Our aim is to add up all the forces from each of the infinitesimal pieces to get, using the principal superposition, to get the electric field. So I'm highlighting this piece over here and a piece opposite to it. The force from this piece acts in this direction, and the force from the diametrically opposite piece goes like this. And so we can resolve them into the x and y axis, which let's call this axis y. This is x, and the one sticking out of the paper is z. So we have x and y axis over here. And so these are the two forces, F1 and F2. And so this components in the x direction, they act in opposite, they are faced opposite. So they act against each other. And because the situation is completely symmetric, the force from these two diametrically opposite points at the center, acting at the center, should be the same. One cannot be larger than the other. So these two components, F1y, F1x, and F2x, must be equal and opposite, and therefore cancel out. And so we should have to only worry about the force in the upper direction, force along the y direction. So we only have to worry about F1 y plus F2 y, and both of these again should be same for symmetry. So this is like 2 F1 y. So what is this force? So let us call this angle theta. Then this is also theta, and then F1y is F1 into cos theta, where F1 is the magnitude of the force, and F1 is the force from this point in orange. So this is, sorry, not the force, I want the field. So this is, what is E1? E1 is charge by r square, so it's lambda dl is the amount of charge contained in this tiny infinitesimal piece by r square into cos theta, where r square is nothing but z square plus r square. So this is r square plus z square. And what is cos theta? So this angle is also theta. So that gives us, this should be, this writing z is like this is, yeah. So this line is z, this line is r. So it is z by square root of r square plus z square. So this thing is lambda z by r square plus z square to the power 3 by 2 into dl. And there's a, I have missed a k here. K is 1 by 4 pi epsilon naught. And finally, we have to integrate this. This is the force due to this tiny piece. I have to integrate all of these pieces. So total magnitude of force is the integration into dl along the length. That's k lambda z by r square plus z square by 3 by 2 integration over dl. So adding up all the pieces. What is integration over dl? I'm integrating over the length of a ring of radius r. What do I get?
2 pi r.
Yes, we get the circumference, which is equal to 2 pi r. Good, good. So the final answer by 4 pi epsilon naught 2 pi r lambda here into z by r square plus z square 3 by 2. Is this correct?
Into 2.
Into 2y?
Because the y coordinate is counted twice, should be counted twice.
Yes, but we integrated over the full length. So this 2 came from when we were adding these two diametrically opposite guys, right? So if we,
Okay, sir. Understood.
okay. So in physics, we always try to check once we have an answer that we obtained by computation, we have to check if that is indeed the right answer by checking some simple scenarios. So what can we check here? How can we check this answer if this is correct by considering some simple scenarios where this answer where we already know the answer.
At z equal to 0.
Z equal to 0 is the center of the center point, and the force there should be 0 because it's getting forces from all directions, equal forces from all directions. So that should cancel. And indeed, we see that there's a Z factor over here. So taking Z is equal to 0 means the electric field goes to 0. So Z equals to 0, E is equal to 0. Check. Any other checks? Z is equal to infinite or Z much greater than R. What does that mean? That means that the force, that the particle is much farther away. So Z is much, much greater than R. What do we expect when Z is much greater than R? What should the field be like when Z is much greater than R?
E is 0.
E is 0, no, it should not be 0. No, no.
Like a point charge.
Like a point charge, correct. So if I go further away, how would I look at the ring? From far distance, I cannot see whether it's a ring or it's just a point. So anything, if you're sufficiently far away, it will look like a tiny point. It won't vanish, but it will look like a point. So the charge, the field due to anything, if I look at it sufficiently far away, if it has some net charge, then from much, much further away, I cannot see its structure. It just looks like a point, and I should see the field due to a point charge. So let's check. So I have lambda by 4 pi epsilon naught 2 pi r z to the power 3 by 2. What I'm saying is z is much, much greater than r, which really means that whenever I add z and r, I can just put r to 0, I can neglect r. Means in this sum is almost equal to z square. So let's make that substitution. So this is just z squared to the power 3 by 2, which is z cube. This cancels to give me z square. So I have 2 pi r lambda by 4 pi epsilon naught z square. 2 pi r lambda is the radius, is the circumference into charge density, which is the total charge. So it's like q by 4 pi epsilon naught. Z is the distance square. So this is just the force due to a point charge. Is this clear? So at large distances, we expect that we cannot see the structure of the charge configuration, whether it's a ring or a ball or whatever. It should just look like a point charge. And so we expect the field to also be the field of a point charge. Questions? Let's do another example. Let's do the disk. Let's do the disk. Okay, let's have a disk of some radius. Radius r, let us say. And then I have a charge sitting a distance z from the center. So how would I go about this? Now I know how to get it for a ring of charge. So I can divide this disk into rings, but not just rings of, not just infinitesimally thin rings that we did last time, but which will have some kind of thickness. So I divide this into rings of very small thickness dr. So let me draw this once again. So this is one of the rings of radius r and thickness dr. And this is sitting inside the disk, and this distance is z. And first we want to calculate the force due to this thin ring, which we already know, kind of know, and we want to add up all the thin rings. So that's how we can calculate the field due to this entire disk. Despite my terrible drawing, this whole disk is supposed to be perpendicular like this, and the four charges, the point is sitting here somewhere over here. It's not tilted as shown in the diagram. Okay. So what is the force due to one of the rings? So it is pretty much the same as what we found here, which was this guy. So let's take this guy. So the only difference now is going to be that instead of lambda, we have a charge density over here, which we call sigma, and we have to multiply 2 pi r with the thickness, which is dr, and z is as it is. And now we have to integrate this. So this is for one of the strips, and now we have to integrate over all the strips. So this integration is sigma 4 pi epsilon naught into 2 pi z. Everything comes out of the integral. And so this integral, integrals I will not do, because integrals are something that one should do in the privacy of their homes, not in public. And so this answer is, I have it written here. So this is from 0 to r. R is the full radius of this object. And the answer is, I have it written right over here, which is z by r square plus z square root. And so this is the force due to a disk of radius r on a charge that is sitting at a distance z from the center of the disk. Is the electric field, magnitude of the electric field. The direction is, you already know, this is the direction. Okay, so for the last thing we will do today, let's just now take this as at a large distance away and see how that works. Right, we should see that for this case also, if I take z to be much, much greater than r, then it should reduce to a point charge. Now, if you do it naively, if you just put r is equal to 0 in this formula, then you just get 0, That would be wrong. So you have to be careful here. Because putting R to 0 like this would just mean that the whole charge is vanishing. You're taking the system to have 0 size, and both the limits of the integration are becoming same if you take R is equal to 0 here naively. So you have to be careful. So how do you do this? So this is sigma by 2 epsilon naught 1 minus 1 over z square plus 1. We write this as sigma by 2 epsilon naught 1 minus 1 plus r by z whole square to the power minus half. Now you can use the binomial series formula. So what is the binomial series formula? It goes like 1 plus x to the power n is 1 plus nx plus dot 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 are higher power terms, n square, x square, x cube, and so on. But if x is very, very small, then x square is much smaller than x, and x cube is much smaller than x square. So we can neglect those terms in an approximation. So using that formula, we get sigma by 2 epsilon naught 1 minus 1 minus r square by 2 z square. So the 1 cancels, and we are left with sigma r square by 4 epsilon naught z square, multiplying pi in both sides. We have pi r square sigma 4 pi epsilon naught. This whole thing, pi r square is the area of the circle, sigma is the charge density, charge per unit area. So this whole thing is charge q. This is 4 pi epsilon naught, and this is the distance, like r square, z square. So again, we have recovered that here also the electric field at large distances falls off like 1 over r squared. So I want to think about this. One thing you should think about is why exactly were we getting the wrong answer when we put r is equal to 0 here naively? What is the interpretation of that? You should ask yourself. And next time we will do Gauss law. So if you have, the class is done. If you have any, I will stop recording now. If you have any questions, you can ask. I'll be here for the next 10 minutes.